Welcome back to another episode of Drawn to Science, and today we're going to talk about mass spectrometry. So right now I'm drawing a mass spectrometer, which is the machine that is used to identify different isotopes, and we're going to talk about what isotopes are later. So the first step to the spectrometer is ionization. Ionization is the process by which an electrical neutral atom loses or gains electrons to become charged ions. This is done by shooting a high energy beam onto the gaseous molecule so that the molecule ends up charged. And this is a necessary step for molecules to be analyzed by the spectrometer. Step 2 is acceleration. In acceleration, these ions are accelerated by extreme kinetic energy so that it can be measured to find where long-lived radioisotopes against the more prevalent, abundant, stable isotopes. Step 3 is deflection. Deflection is the process where a magnetic or electric field bends the path of the accelerated ions. Lighter ions are deflected more compared to the heavier ions due to their mass. It's the mass that separates them, not the charge. The last step is detection. This is where the ions are detected for their mass over charge ratio, or otherwise called the M/Z ratio. This is when the spectrometer identifies the secret identity of the ion. Mass spectrometry is a way to combine different isotopes and find the average atomic mass. For example, hydrogen has 3 different isotopes. It has protium, deuterium, and tritium. Protium has a mass number of 1, deuterium 2, and tritium 3. This is due to their differences in neutrons. They all share 1 electron, 1 proton, which is their ID card, saying that they're hydrogen. But deuterium has 1 neutron, while tritium has 2 neutrons. This impacts the mass number because mass number is proton plus neutron, and electrons don't count because they're too light. If you look at a periodic table, you'll see that there's a mass number, and it's in decimals, usually long decimals. This is because this is the average of the atomic masses based on the abundance of the different isotopes. For hydrogen, it's really close to 1 because protium is 99.98% of all the isotopes of hydrogen, while deuterium is only 0.015 and tritium barely exists. Mass spectrometry usually shows up in questions where you have to find the average atomic mass. So if you're given a table of the chlorine isotopes, for example, you're going to be given the mass and its abundance in percentage. All you have to do is apply it to the equation where you multiply mass 1 by percentage 1 plus mass 2 times percentage 2. In this case, it would be 34.97 times 0.75, the decimal form of the percentage, plus 36.97 times 0.24. This will equal to 35.44, which is the average atomic mass of chlorine. You will also come across a graph, which just looks like bars of lines. On the y-axis will be the abundance, and the x-axis will be the mass of the different isotopes. So for chlorine, the graph would look something like this because chlorine 35 is more abundant than chlorine 37. Just from the graph, even if you're not given the table, you should be able to solve the same thing. The graph can also be used to determine how many isotopes exist of the specific chemical element. Thanks for listening.